Thank you very much. I apologize to those of you who have heard me talk about this before, because, well, there will not be anything entirely new, but hopefully you will still enjoy it. So what is this about? This, in a way, what I'm going to talk about goes back to Axe's characterization of the theory of finite fields, and in particular, his definition of what is going to, well, I think he already called it this way, so the class of pseudo-algebraically closed fields. And why is it relevant to the theory of finite fields is because of Langevin, well, I mean, I'm going to define it, but then we'll see. Because of the Langevin estimates, this is part of the theory of an ultra product of a non-principal ultra product of a finite field. So what does it say? So K, during all this board, and probably the next board, K will be a field, and it's pack if and only if. Whenever you take W, a variety over K, which is geometrically integral, then there's a point. Okay, so this geometric integrity appeared briefly earlier this week. Well, it was geometric irreducibility, I guess, in your talk. But it's essentially what you're asking is that the is non-empty. Thanks. A variety is geometrically integral if it's irreducible, and when you go up to the algebraic closure, it stays irreducible, and in fact, it's a bit more than this, because you want to preserve integrity. But maybe another way to see this is that W is geometrically integral if, so if K is characteristic 0, well, okay, is if and only if the function field of the variety, this is a regular extension. Okay, so if you don't know what a regular extension, this is not helping you much, I guess. But in characteristic 0, they're very easy to describe. So if K is characteristic 0, although I won't need characteristic 0 in this talk, this is the same as saying, so regular is the same as saying that KW intersected with the algebraic closure of K is exactly K. Okay, so these are essentially varieties whose function field does not add any algebraic points over the base field. And so a field is PAC if whenever you have a geometrically integral variety over it, it has a point. There's an equivalent way to formulate this in more model theoretical terms, which will involve this question of regular extension. So this is the same as whenever you have a regular extension, then it is existentially closed as rings. So just so that we're all on the same page, existentially closed means that whenever you take a quantifier free formula in the language of rings, so essentially zeros of polynomials, well, and non-zeros of, I mean, this is the same as asking that whenever you have a collection of polynomials, if they have a 0 in some extension, they have a 0 in K. I mean, there's some things to do about negations and unions, but you can get around this. So this is really reasonably easily seen to be the same thing. Yes, and so these two notions, well, I mean, this one notion became a very important notion, for example, I mean, in various fields, because in particular, it is part of being pseudo-finite, but also it became one of the main examples of model theoretic unstable behavior. So model theorists have and looked at them a lot. But a packed field somehow has very little arithmetic. So it cannot have any order, and it cannot have any p-adic valuations. And so people also started asking themselves, well, can we do something a bit like that, but where we take orders in account? And so then came up the class of PRC fields, so pseudo-real closed fields, which is more or less the same, except now we take orders in account. So how are we going to take the orders in account? So again, W is a variety over K, geometrically integral. And you assume that for all L, well, no, let me call it F. For all F real closed containing K, if, no, sorry, W of F, well, let me add that W is smooth to avoid problems. If you have a point in every real closure, then you have a point in K. Okay, so this is pseudo-real closed. If you think for a second about it, a silly way of saying that you are packed is that if you have a point in every algebraic closure, then you have a point. Okay, so this is really the same thing, except now we take the orders in account. And this can also be, sorry, I think my parenthesis was meant to be there, but I don't know what. This can also be rephrased in terms of extensions. So whenever you have a regular extension, which is totally real, meaning that every order extends, then it's existentially closed as rings. So once again, I'm specifying in what language I'm working. For now, maybe it's not completely, I mean, maybe here we're starting to see why I specify as rings, because we might be wondering what about the orders. But really, I'm just asking existentially closed as rings for now.
Can I ask about the parentheses?
Yes.
So you're saying you're saying that if W has a point in any real,
in every real closed field containing K, then it has a point in K.
Okay, so then maybe the parentheses should be then the other place.
Yeah, I don't know what's the clearest, but
the hypothesis, the for all is in the.
Then.
But it's not just a condition for each F. You assume that for all F's. And then
Yes. If for all F blah blah blah, then yes, then maybe that's why I wanted parentheses around the first one. So yeah, you need to check all the real closures in the same way that you need to check that every order extends. It's really this is what PRC is about. Okay, so in particular, you can also check that if a packed field is exactly a PRC field without any order on it. But I mean, this is not a very a particularly enlightening remark. So let me see if I can get some color. No, green is not a good idea. Let's say red. You can do a similar thing if you want p-adic valuations. This is called pseudo-T-adically closed. And you replace real closure by p-adically closed. And you replace every p-adic valuation extent. So here we start having, so I'm just putting it as a parallel, but here, of course, you can start wondering how ramified do I allow my p-adic valuations to be. So for now, let's say p-adic valuations are unramified. But of course, you can do variations on this where you allow a bit of ramification. But anyway, so you can do a similar thing with valuations. And then, of course, when you see that, one is led to wonder can we talk about both orders and valuations at the same time? One, for example, being Lau in his PhD thesis. But, and so there have been numerous attempts at finding a setup that talks both about orders and valuations. Yes?
Yeah, it's a well-developed theory. It's the theory of quasi-ordered fields that covers both orders and valuations.
Yes, I mean, that's, I was about to say that there has been multiple ways to do this, and I'm going to present another one. But there's also other ways to do it. I mean, anyway, so yes.
Are PXD fields automatically PRC?
No, well, yes, because they don't have orders and they don't have p-adic valuations.
So you don't require a PRC. You just maybe you said this already. You don't require a PRC
to have an order. No.
To have any ordering at all.
Yeah. So in particular, this is included in this. Okay. In either versions. But then, so there's been multiple ways of doing this, and so for reasons that will become apparent later, Sami and I, well, we wrote a paper on PPC fields about some other theoretic questions about it, and it was a bit frustrating because the proofs, they're essentially the same in the PRC field and the PPC case, and we were like, I mean, there must be a common proof. And so we decided to embark on a little adventure, which was to define what became the class of PTC fields. So let me set up a little notation. So here, L will be a language that contains the language of rings. So if, for your peace of mind, you can assume it is the language of rings if you want. And T is an L theory of large fields. For example, a completely innocuous and innocent example given the second column, it could be the theory of real closed fields. But it could be something else. So you take an L theory of large fields. So large is something that looks a bit like PAC, but not exactly, which says that if you have W geometrically reducible, integral, sorry, over K, and if it has one point, then it has Zariski-dense many.
Smooth one.
Yeah, sorry. Smooth geometrically integral. Okay, so PAC fields are large, but real closed fields are large. In fact, PRC fields are large. And many henselian fields are large in general. I mean, there's many, this notion has had many names over the years. Maybe as a Parisian mathematician, I should be calling them fertile, but I don't think this is a reasonable name, so they will be large. Well, okay, core fertile is a bit odd for me, but whatever. Anyway, this being said, this T here is the same as this T. Okay, and so now, well, we can do the same thing. If and only if I take W, a variety over K, which is geometrically geometry integral smooth, and if, so for F, model of T containing K, so here secretly K now is an L structure. But as I told you, you can assume K is just the ring language, and so if you want, it won't change much. So whenever you take F, model of T that contains K, W of F is non-empty, implies W of K is non-empty. So same definition, except now T is whatever you want. And yeah, so maybe I can give examples. So if you take T to be RCF, well, no, let's start with even easier. if you take T to be ACF, so the theory of algebraically closed fields, then, as I noted earlier, the PTC fields are exactly pack fields. Okay? But now if you take T to be RCF, the PTC fields, so RCF in the language of ring, this is important. PTC fields are exactly PRC fields. Now if you take T to be the theory of of p-adically closed fields, then you get PPC fields. I think you're getting the idea. Maybe just to give you a small example of why I was keen on allowing a slightly more language. If you look at RCF with the order, so you name the order in RCF, then PTC fields is what's called one PRC field, which is PRC fields with just one order. This is not completely obvious from the definition. This requires a theorem or a lemma, I don't know. But this requires a little something. You have to show that on a PTC field where T is RCF with one order, you don't have any other orders. So you have to show a little something.
When you say K is an L structure, you mean K is the model of T for all?
No.
So, no? You want an ordering, right?
No.
So
Because
PAC is still one PRC includes PAC?
no, it doesn't, because here I want to.
So you want an order.
Oh yes, you're right.
You want the model for all, yeah?
Otherwise, it's one PRC or PAC. I agree. Yes, yes. Then you can try to be a little more sneaky, and you can try looking at what I want to write as the disjunction of a bunch of RCF with the order names, right? Which, so this is weird notation, but I mean, I don't know standard notation for this. A model of T is exactly a model of one of the things, but I don't care about the rest of the symbols. Okay, so your model of T is your model of one of the RCFIs, and maybe the other orders are not orders anymore, they're just nonsense. But in particular, your T, to start with, has infinite. Well, so, okay. Then I don't really want that, but whatever. What? Yes, I choose n copies of RCF. And I just bundle them together without really caring how they interact. And then PTC fields. So let me remove this assumption so that I don't say anything wrong. So this was like at most one order, and this is at most an order. Okay, so now typically you will have an order on your field K, and then exactly those you only check those real closures, and the others will disappear because well, you can't have any other orders on it for reasons that maybe we'll see later. But anyway, now you see how you could start doing mixes of stuff, because here I chose RCFI, but I could decide to put PPC for some of the coordinates, and then I would start mixing orders and p-adic valuations. I could choose my favorite theory of henselian fields instead of PPC, and I could start mixing stuff up. And I get a bunch of classes that I can try to understand. So there's one line that I haven't filled in yet, which is that there is also a model theoretic version of this. So if you take K, L, regular, totality, so I haven't told you what this is, then it is EC as rings. And so now I really want to specify as rings because now we have more structure around, we clearly have more structure around, and I really just want existentially closed as ring. What is totality? You have to think a bit how to do, because now it's not clear that there are orders around you want to extend or things like that. So an extension is totality if whenever K is inside the model of T, so I have my two extensions, then there exists a ring embedding into some elementary extension of F. Okay, so, I mean, of course you can't expect it to live in any model of T, there are size problems, but you can expect it to live in an elementary extension. And so if your theory were RCF, you can check that being totality is exactly all the orders extend. But now we define this without mentioning any arithmetic structure at all. Sorry, I forgot the T. Over F, over K. Thanks. Yeah, otherwise it's nonsense. So, okay, so here we are. We have defined a nice class. Now we want to prove things about it. And so, if you look a bit, for example, at Sami's work, or, well, at least that's where we started from. In the PRC case, something that she uses mostly implicitly, but that she does use a lot, is that we can improve this statement a bit. Because as I stated, it's a bit odd. We're only looking at existentially closed as rings, and this is a bit odd. But in fact, Presto, so I think the statement I'm going to give is Presto, but maybe he only proved it with restrictions on the number of orders. I'm not 100% sure, but morally it's Presto. If you have, so if you're PRC and you have a regular extension which is totally real, then you are EC as a multi-ordered field. Ordered ring, I mean, whatever. Meaning that you work in the language of the ring with, after having named the orders. Well, how many orders you want, actually. So, since you can do it for, I mean, or just all the orders, if you want. I mean, existentially closed is a finitary notion, so you only need to check it finitely many orders by finitely many orders.
So this means on L you pick an extension of each order?
Yes, sorry, yes, of course. I chose an order on L. Yes. So here L now is also comes with this structure. So if yeah, of course. So whenever I have an extension of multi-ordered rings, which is totally real, then it's EC as a multi-ordered ring. Okay? And so you might be wondering, what about the pack case? And then now it's not clear what you want to prove because, well, a pack, as I told you, pack structures don't come with any arithmetic information, but you could decide, for example, to just put a valuation on your pack field. Why not? And then it's really not, it was open for a long time whether the similar statement holds, and it was settled by Kollar that, so if you have a regular extension and V is a valuation on L, then you're existentially closed as valued field. I mean, I write valued rings, it is the same. It doesn't matter.
From when roundabout stuff is out of
Well, 2004 maybe. So it's a question in field arithmetic, the book. What? Yes. Yes, yes, you're right. Non-trivial on K. Thanks. Otherwise, it's a bit false. Okay. Well, as you can guess, Kollar didn't prove that result, but he proved the geometric version, which I'm going to write now. I mean, they're equivalent, but so I guess he proved that result, but that's not how it's stated. So it's a statement about approximating points in varieties over a packed field. So to do the same thing, you take K and V evaluation on K, non-trivial. Then it's then NW geometrically integral over K. Then W of K is actually valuation dense inside W of K arch, where you choose your extension of the valuation to the algebraic closure. Okay, so you can also define the same thing for, well, you can do the same, you can play the same game for PRC fields. And so now what you get is that if W is geometrically integral smooth, and K, then for all, well, let me see how I want to write it. Well, so we saw that this is non-empty up there. Totally real. I did not define what totally real means for a variety, I guess, but it's that this is the assumption totally real, the thing in the parentheses. Okay, so it has a point in every real closure. So if W is geometrically integral smooth totally real, then you can find a point arbitrarily close. Well, so let me actually write it properly. So now you choose Fi for I smaller than n, the real closures of K, and you take OI inside of W Fi open for the, well, for the ith order. Then the intersection of these opens with K is non-empty. Okay, so this is an approximation statement, which tells you that you can find actually. What? Yes, thank you. That you can find points in WK that are as close as points in finitely many localization you choose.
So this is the same, I guess, as saying that WK is dense in the product of the WO.
Yes.
But I guess it has much more, right? In the infinite case, you have block approximation.
Yeah. But for now, let's. No, I agree. You have more. But at least you have that, which is equivalent to this. I mean, you can do better, of course. I agree. So then the question is, what is the same for my PTC class? And then again, we have the problem that there's no natural topology around. For if we just start with the theory T, there's no reason that there's a natural topology around. But if you see what I was doing. I really want to consider completions of T as my localizations. So what I'm going to do is choose a bunch of completions of T and assume that they have a topology and see what happens. So this is going to be a definition for now. So I'm going to define, so let's, so some more notation that will go on this board. So fix a bunch of theories Ti. I is allowed to be infinite. I can choose infinitely many localization if I want. And they have a few properties. So they have quantifier elimination. They have, they come with a definable V topology, henselian V topology. I'm going to define what I mean by that I'm going to write to I. Is that all I want? Let me check. T. Yes, these are Li theories where Li extends the ring language. So you might be wondering why they don't extend L. It's for technical and silly reasons. Well, maybe you see it in that case. You don't want to have the other orders. So you've chosen this bunch of theory. I think I have not forgotten any assumptions. Yeah, so what is this definable henselian V topological thing? So a V topology is a topology on a field that's induced by a valuation or an order. There is an intrinsic characterization of it, but I don't think we need to know it here. It's said to be henselian in something like the henselian, the Hensel's lemma hold, or if you want to be fancy, something like the implicit function theorem for étale morphisms. And you say it's definable if you have a definable basis of, if you have a definable family that gives you a basis for the topology. In Ti. In the model of Ti? Well, in the theory, so yes, so in any model. It's always the same. The family is zero definable, and you get a topology in any model of Ti. Okay, and so now I'm going to add letters together. I'm going to say that something is PTC localized at I, or whatever, PTC I. If whenever, so now I want to make sure that the TIs, I actually have localizations for the TIs, so I'm going to assume that this is a model, so what I did not do earlier. This is a model of the universal theory of all of the of each of the TIs, so it has a localization in this sense, although it's not quite clear what it means, but let's go with the analogy. And yes, then K is PTC I, if and only if, for all W, geometrically integral smooth, over K. And OI inside W of KI. So this is just a model of Ti that contains K. Here you start seeing why my quantifier elimination assumption matters, because you eliminate quantifiers, it doesn't matter which Ki you choose. The existence, they will all be essentially the same. I mean, of course, there's non-standard issues, but this is something that makes sense over K because my theory T eliminates quantifiers. So if you take your OI, which are, now I assume that they're LIK definable. Okay, so in particular, they're definable without quantifiers in Li. Then, the same as before. The intersection of all the OIs, so finitely many, sorry. I here is inside I0, where I0 inside of I is finite. Okay, I can only approximate for finitely many at the same time. This intersected with WK is non-empty. So for now, it's a definition.
Can you assume that OI are non-empty?
Yes. Non-empty. Yeah, of course, otherwise there's no chance. Ah, sorry, I wrote in the wrong whatever. Wrong line. But yes, so here OI was non-empty. Of course, otherwise this makes no sense. Well, otherwise the class is very empty. So non-empty tau I open. What?
They are open, the OI?
Yes, tau I open. I forgot to write it, but so really the same thing as here. You take opens for your definable topology, and you assume they're non-empty, and then you find points that live in all of them, finitely many of them. But you can do this for an infinite I if you want. Okay, so we want, I would like it to be equivalent to some existentially closed statement. I need a little something, because an existential closure statement will have to talk about all Li definable sets, so I need to know that not too far from being the topology. So I will add an assumption on Ti that I did forget. We asked that we further ask that in F model of Ti, if X is definable, it has non-empty interior. So tau non-empty tau I interior inside its Zariski closure. Okay, because of course, if you live inside a variety, there's no reason you're open for the topology. But if you relativize to whatever variety you live in, you want it to be open. So that essentially every set is essentially an open of a variety. Every definable set is an open of a variety. And if you have that, you have, so imagine the lines are reversed. If you have, this is equivalent, so if and only if for all k inside of L totally T, of course this needs to be a model of the union of the Ti folds. Sorry. L, a model of the union of the Ti folds. So L also comes with a structure for each Li. Then, so am I not forgetting anything? Then you're existentially closed as union over I of the Li structures. Okay, so these two are equivalent, but I'm not saying that I don't know what relation they have to PTC. Of course, it's not very hard to see that this is stronger than PTC. Just take OI to be the variety itself. And so you get, this is stronger than PTC. Given the other cases, we would like the same miracle to happen again, which is that we would like that being existentially closed as ring somehow allows you to be existentially closed as Li structures again. And this miracle does happen. So this is the first theorem I wanted to state for today. I put none. I should probably, if I is infinite, I should definitely put some. So I want models of T to be models of Ti can be made into models, can be enriched into models of T. Again, if you consider that T is just the ring language, you don't have to do all this gymnastics, and you just say that models of Ti are models of T. So if we are just assuming L is in the ring language, you're just asking that models of Ti are models of T. Actually, if your I is finite, you could easily just add them to T so that this is an easy assumption to ensure. Yes?
To define the Henselian p-topology, you asked that there is a uniform definition across all modes of Ti?
Yes. The definable topology is in Ti.
It's always definable.
Yes, okay, no, I want uniformly, so this is a notion for the theory, not for the models. I want it definable in the theory. So yes, so uniformly. So there's a zero definable family that works for all models. Okay, so now I can write my first theorem, which is that essentially what you expect is true with a number of caveats. So theorem, K is PTCI if and only if K is PTC. Sorry. Under a strong finiteness assumption. So let me explain what assumption I want. So in fact, you can do a little better, but let's assume. Okay. What the assumption we may assume that T is the disjoint union of the Ti's, if you want, and that I is finite. You can do a little better than that, but it doesn't really matter for this talk. So assume that the models of T are exactly the models of one of the Ti's, and that I is finite. Otherwise, this is not a theory. Then your PTCI, if and only if K is PTC, the tau I are independent, well, distinct suffices, on K, plus two technical assumptions that I'm going to write for the sake of completion, but they're in the equivalence anyway, but something odd could happen with the definable closure in the ith language. And you want this to be inside, you want K to kind of be aware of it, so you need it to be in the algebraic closure. And also, it could be that the models of Ti have infinitesimals compared to T, so you have to address that problem. And so you ask that, essentially you ask PTCI, but for A1. So if OI inside Ki is LK definable, then non-empty, then OI intersect K is non-empty. So what you want to avoid is that there are K definable infinitesimal open sets. So this is an equivalence. Okay, so in the case of real closed fields, or at least you don't get as good a theorem as the one I wrote here because I have finiteness assumptions, but you still recover it because those two things are always true for RCF, for example. So you just get that the K is PTC if and only if the topologies are distinct. Yes?
I understand. So you interpret Kollar's theorem as a theorem on ACVF.
Yes. Kollar's theorem is a theorem on ACVF, yes. So this is saying that, yes, or maybe I should have, this is saying, so this corresponds to taking T to be ACF, well, ACVF really, and T equals T1 is ACVF. Or really T is ACF and T0, yeah, okay, let's do it this way, this is cleaner. T is ACF and T0 is ACVF. Yes?
Correctly, you said before that you don't want to assume the Li and L to be comparable. So what structure is there on K in this theorem?
So yes, so sorry, I should have said that. K comes with, is an Li structure. This is a union of the Li structure. No, an L also.
Also L structure.
Yeah, yeah. I see all my languages. Because otherwise this is blatantly false. If they're the same, you can easily find two open for the same topology that don't intersect. So you need the topologies to be distinct for this to have any chance of being true.
I mean, L was distinct, you mean?
Yes, pairwise.
And non-trivial, not discrete.
Yeah, okay. Non-discrete. Good. So how late am I? I'm late. So maybe so I've talked about two of the first words in my title. I would like to finish to give a brief account of what this NTP2 nonsense is about, which was what the reasons why this whole project started, which is that, in fact, well, why we wanted to prove this approximation theorem is that we thought, given Sami's proof, that if we knew this approximation theorem, there was a good chance we could describe the model theory of those things. And so that's what we embarked on doing. And in particular, the main question we were asking is, how do these things fit in the Kollar classification? So I'm going to start to say model theoretic swear words, but I will define the relevant ones. So just for the pack fields, just that we all agree. So if K is pack, and then I'm just going to add perfect bounded. Otherwise, it gets more complicated. So bounded means that there's only finitely many extensions of a given degree for every degree. So the Galois group is small. Then K is super simple of U rank 1. Yes, I know I should say U rank not. Sami's main theorem in her PhD thesis is that if you take K NPRC or NPPC, it works the same. So with only, well, okay, PRC bounded. If you're PRC bounded, then you automatically have finitely many orders, because there's only finitely many involutions you can look at. So if K is PRC bounded, then K is NTP2 of burden N. So now I'll try to quickly explain what this burden thing is, which is because this is the last theorem now. Yes, sorry. Of burden, the number of orders. N, where N is the number of orders. So what is this burden thing? I need to erase. I've not managed to not erase, damn it. Yes, so what is this burden? So it's meant as a combinatorial definition of dimension. So if you start with X, a definable set, in some theory, in some structure M, well, I'll assume M to be a bit saturated, but and you say that the burden of X is greater than kappa, so kappa is some cardinal. The burden is greater than kappa if you can find phi of x ai j, where I is smaller than kappa and j is smaller than omega. So you with phi I m a I j inside X. So you find a collection of definable subsets inside of there, such that two things happen. So you have some inconsistency. So if you take, if you fix an I, hopefully I'm not gonna get it in the wrong order. So did I write it in the same order? IJ, yes. So if it, yes, so fix, if for all I, phi m, well, phi x aij, as j varies, is ki inconsistent for some ki, which only depends on I. And for all f from k into omega, well, so now you want to do, we were looking at lines, now you want to look at columns, you want to do something a bit more subtle than this, which is that you want to move in your columns. You can, this set here, sorry, Fii is consistent. Yes, there was 1 in 2 chances. Okay, so this is consistent. So what are two natural sources of burden that I know of, which maybe illuminate a bit this notion? If you have x inside of the nth Cartesian power, you can look at hyperplanes for each variable. Okay, so you can look at xij, which is xi equals aij. Okay, you look at hyperplanes like this. So if you take two of them, they don't have an intersection along lines. And if you take any choice of them, so here j is smaller than, no, sorry, I is smaller than n. If you take any n of them, they have an intersection, which is just the point aij. Oh, well, the tuple in question. So this is one source of burden, which is just like good old dimension, I mean arity. Another source of burden is that if you have n independent definable topologies, and x is inside the home sort, then you can also find a pattern like this by just taking families of opens that don't intersect. Okay, so you take O I j with I still lesser than n, pairwise. How do you say pairwise? What? Disjoint. Thanks. Pairwise disjoint open. If you take along a line, well, they're pairwise disjoint. And if you choose them along the columns in any way you want, because the topologies are independent, this is exactly saying that you have an intersection. So this is another source of burden. So in a way, in our case, well, we expect at least those two sources of burden. And in fact, what could happen is that in the TIs, you have more burden. And so the last theorem, and I think I'm at, yeah, so under the same assumption as before, so I'm really working in the finite every case. K is T is the union of the Ti, I is finite. And so if K is perfect, PTCI, bounded. So before I was only computing the burden of the affine line, but you can do more than that. Then you can show that the burden of any x definable, the burden of any x is the sum of the burden you expect from each series. So what do you expect this burden to be? So where dimension of x equals d. Here, dimension is really Zariski dimension of the is a crude dimension of the Zariski closure. Sum over I. So this is the burden that you get essentially from RET in each theory, and you sum them, and you get the full burden of x. So in particular, if you're starting with A1, you get burden of A1 is the sum of the burden. So this is usually called the burden of K, of the burden of the Ki's. So here the burden is computed in the I theory, of course. Just to quickly conclude, if we put all of this together, we get a nice theorem, and I think. One? Well, the thing is that I really need my TIs for this to make sense. So.
You didn't say anything about PPC. Is NTP2 or burden something?
In PRC, you mean? In PPC, this is a particular case of that theorem if you want, but also Sami proved it. But you notice I've stopped doing the p-adic equivalence at some point. But you have the same theorem. The burden is the number of p-adic valuations. But so if we put all of this together, we get one last example. So if you start with K, PAC, perfect bounded. And you take VI, independent valuations. Then the first theorem tells you that you're really PTCI for the CVF associated to these valuations. And the second theorem tells you that the burden is the sum of the burden computed in the ACVF. So the burden of K is the number of, well, it's N. Okay, which I think, well, which is a nice example where everything fits together. Of course, this is one among infinitely many examples, because you could do whatever you want with your T's and your Ti's and get a variety of theorems for this. There was this word NTP2 on the board that in the title and on the board. NTP2 is bounded burden. So the burden, is that you can't find arbitrary large things with kappa here. I mean, you can't find patterns with arbitrary large kappas. This is being NTP2. So in particular, when it's finite, it's NTP2. Okay, this is all I wanted to say.
What questions, first of all? Can you give some more examples for these PTC fields, PTC and PTCI fields? So I guess I'm wondering I've had some trouble keeping track of all the hypotheses on the TI, and I guess if you have plain valuations and orderings, then you get stuff like Yashov's and Danier's fields of the local global principle with respect to a bunch of valuations.
Yeah.
And we also have approximation theorems.
Yes.
So I wanted to ask if you have something essentially different in mind.
No. So in particular, you recover Pop's classically closed fields or whatever easily. I don't know if this, but I think one main distinction between our work and what was done earlier is that you can add valuations, arbitrary valuations. Mm-hmm. So we can deal with the localization being a CVF, which is not the case in all these theorems because this is harder. So yes, I should point out that here I have my finiteness hypothesis. If you know that none of the localizations are separably closed, then actually none of the models of T are separably closed, then you can prove this theorem without the finiteness hypothesis. This was done by Schmidt at some point. I think the main new thing here is the separably closed localizations. I don't know if that answers your question.
Yeah, yes, absolutely.
So of course now the thing to do is to do it with infinitely many and separably closed localizations. But
I mean, could you infer the result for this independent derivation from Kollar's that you have identity, or is
no. You need. I mean, the proof of this is looking long at the proof of Kollar and seeing what happens when you have multiple topologies. But you need to adapt the proof. And in fact, Will Johnson has a similar proof where he assumes that K is henselian and then you put arbitrary valuations new arbitrary other valuations on top of it. And I mean, the proofs kind of look the same. The hard input from Kollar is to show at some point. I mean, so you prove it for curves, and so you find a nice. You see your curve as a nice covering of P1, and then you do stuff, but at some point you need to show that something is geometrically integral, and this is the hard part, at least for most model theorists, and I think that's why this stayed open for long, is that you have to show that a certain variety is geometrically integral, and it's not, I mean, well, that's the main input, I think, from Kollar. And then if you put everything back together, knowing that this variety is geometrically integral, you get to things where you can start having more than one valuation.
More questions?
Yes.
So, if I remember correctly, in PRC, I think I showed that PAC is interpretable, and so is it the same true for PTC then?
No.
Always at least in some PAC, like it's not NIP, or could it be NIP?
No, so this is hard.
Okay.
We don't know. So it's a bit annoying because, of course, when you take algebraic extensions of PTC fields, they're not PTC anymore because the T's might change. Okay, you need to do something. I mean, there's obvious conjectures you can make, which is that you look at T, you look at the possible algebraic extensions of it, and you say stuff about it, but it's not quite clear to me how it works. And in particular, we don't know the converse. So we don't know that being NTP2 implies having bounded Galois group, which is known for PAC. It's known for PRC because if you add I, you get a PAC field, and so this is you can easily see this. But in this case, I don't know the converses. So even for PPC, the converse is not known. But sorry.
Yeah, okay, let's not comment. Thank you. We continue at 10.